So 8.4 focuses on sort of two ways that we can describe acids and bases, and that is strong versus weak. And so strong doesn't necessarily mean concentrated. So a lot of people will confuse strong and weak with like concentrated and dilute. They're two different things. So concentration has to do with the molarity, okay? Strong and weak has to do with if they completely ionize or dissociate. And so the words ionize or dissociate kind of get used interchangeably. So just make sure you recognize both of them. And what this means, if something dissociates in solution, that means if I normally have, you know, like HCl, what's going to happen is it's going to split, and I'm going to have hydrogen ions floating around, and I'm going to have chloride ions floating around in the water, in the aqueous solution. Okay. If something does not dissociate, then it's not going to split apart. It's going to stay in a molecule. Okay. And so things that are strong acids or strong bases, all of their particles are going to break apart into these individual ions. And so there's going to be a lot of hydrogen ions, and then the negative ions around if it's a strong acid. If it's a strong base, like down here, there's going to be a lot of hydroxide ions floating around with whatever the positive ion is. Okay, so this is what makes one of the properties that strong acids and bases have is these are the ones that are the very extreme pHs. So like strong acids tend to be on the lower side, like more like 0, 1, 2 on the scale, and strong bases tend to be on the very high side, you know, like 12, 13, 14. Okay. The weak acids and bases are going to be closer to neutral because there's going to be a lower concentration of either the hydrogen or the hydroxide ion. Okay. So on the example that's on here, they have hydrochloric acid. That's pretty much the most common strong acid. There are some other ones, but hydrochloric acid is pretty much the go-to one when you're trying to, you know, show an example for a strong acid. And so what happens when you have a strong acid like hydrochloric acid is when you dissolve it in water, it completely breaks apart. You have all hydrogen ions and all chloride ions. There's no more HCl left bonded together, okay? And so that's what makes it strong, is that it has a high concentration of these hydrogen ions in the solution. Weak acids or weak bases, on the other hand, they're only going to partially ionize. So some of the molecule is going to split apart into the like hydrogen ions and then whatever the negative ion is, or in the case of a weak base down here, this one has hydroxide and then this other positive ion. So they're going to still, part of them are going to split apart, but not the amount of a strong acid or a strong base. And so what happens is when you see equations for weak acids and bases, typically you use the double arrow because they can go either direction, because weak acids and bases, it can dissociate, but then also those products, the ions, can actually reform and they can make more of the molecule. Okay. And so typically strong acids and bases, when we write their equations, they get a regular yield arrow because we're assuming that all of it's ionizing. There's no more HCl left in that example. For weak ones, we use the double-headed arrow like we do for equilibrium equations because it technically can go either way, okay, because they only partially ionize. So in terms of like our Bronsted-Lowry and our conjugate acid base stuff from last time, strong acids, they are good proton donors because if they're strong, they're going to completely dissociate. So they're going to have lots of hydrogen ions that they can give away and donate. Okay. And because they are strong acids, if you have a strong acid, the conjugate base for a strong acid is always going to be a weak conjugate base. Okay. So for example, if I was looking up at this first equation, HCl is a strong acid. And so its conjugate base would be the chloride, because that's what happens after it donates the hydrogen ion, it becomes Cl minus. And so this is a weak conjugate base compared to other conjugate bases. And that's basically what it says right here. Okay. All right. So when you have these are actually dissolving in water. So what we've done on these first equations is we just left the water molecule out. We just didn't even include it. So what's happening on this third equation right here is, if I can get the green to go, there we go, is that here's the HCl and here is my conjugate base, right? So this is my acid, this is my conjugate base, okay? In this case, water is acting like the base because it's accepting a proton, so this is the conjugate acid. And so what we're doing is on this one, we have the water molecule, so notice it's H3O+, okay? On this first one, it's just H plus because we left the H2O out. We didn't write the H2O as a reactant. So you can represent it either way. If you actually include the water as one of the reactants, then instead of H plus on the product side, you'll have the H3O plus like this. And that's how you can get the equation. So where you can see like the conjugate acids and the conjugate bases, okay? On the flip side, just like strong acids have weak conjugate bases, well, weak acids, they have strong conjugate bases. They are poor proton donors. They don't give away their protons very easily because they don't fully dissociate, okay? So here's my acid, and then this is its conjugate base, and this is a strong conjugate base, okay? It's stronger than the Cl minus from the other example, okay? And so in this case, acid would be, I'm sorry, water would be acting like the base. And then here's that conjugate acid again, the hydronium ion. So bases, I mean, the basic concept is the same. If it's a strong base, it completely ionizes or dissociates. If it's a weak base, it partially ionizes or dissociates. You're still going to have, you know, the regular arrow for the strong ones, the equilibrium double arrow for the weak ones. What's going to be different on this one is that instead of producing hydrogen ions, we're going to be producing hydroxide ions because we're talking about bases, not acids. And so that's why over here you can see the hydroxide ion here. For the equation where we've added the water in. So here's NH3 ammonia, that's my base. And so here it's accepted a proton, so that's the conjugate acid, the NH4 plus. And so water in this case is acting like the acid, so the hydroxide ion is the conjugate base, okay? Strong bases are good proton acceptors. So strong bases like sodium hydroxide up here, they really want to accept another proton, okay? And so their conjugate acids are weak. And so for example, the base for this one is the NaOH, this was the conjugate acid, and so this would be a strong conjugate acid. On the NH3, that's a weak base, and so its conjugate acid is going to be a strong conjugate acid, okay? And that's basically kind of what it's summarizing here. It's at the top of the next page. So weak bases, poor proton acceptors, and their conjugate acids are stronger. And so NH4 plus here is a stronger acid than the OH minus in the other one. So here there's a table. So if you have a strong or weak acid or a strong or weak base, the degree of dissociation, ionization, what you're looking for there is like full or partial. Okay, so full would be the strong ones, partial would be for the weak ones. And then the strength of the conjugate acid and base, you can look back up in the notes to see, you know, if the acid was strong or weak, is the base going to be conjugate base going to be strong or weak? And then same thing for the bases and their conjugate acids. So one way that we can use this in the lab is we can test using electrical conductivity to see if something is going to be a stronger or a weaker acid or base. And so when things are strong acids and bases, they have a higher concentration of mobile ions because the acids are going to have more hydrogen ions, the bases are going to have more hydroxide ions floating around in their solution. The more ions they have moving around, the more they can conduct electricity, because the more charged particles you have floating around in the solution, the more you're able to conduct electricity better, okay? And so in these two pictures, which of these two pictures do you think would be a weak acid or base, and which one do you think would be a strong acid or base? Anybody have an idea? So what's the difference between the two pictures?
What's the strong?
Oh, okay. Sorry. Y'all all started talking at once.
Wouldn't the strong acid and base be at the right?
Yes. So this one is going to be strong. Now I can't tell just from this picture if it's an acid or base. I'd have to maybe test with some pH paper or a pH meter or something like that, or litmus paper. But I can tell that that one's strong and this one is weak because it is lit up. It's just very, very faint. You can just barely see it lighting up there. So strong acids and bases or any strong solution, strong, we call these electrolytes. So any strong electrolyte is going to have more mobile ions and therefore can conduct electricity better. And therefore, if we connect it to a circuit that's connected to a light bulb, the light bulb is going to give off more light. It's going to be brighter. Weak, the bulb will still light up, but it's not going to be as bright. And then there are solutions called non-electrolytes, like sugar water, that they don't conduct electricity at all because they don't have mobile ions. They just have molecules moving around that don't have charges. And so non-electrolytes, the light bulb wouldn't light up at all. Another way, especially for strong acids, now this doesn't really apply to bases, but for strong acids, they have a higher rate of reaction with reactive metals. So as long as you have equal concentration, so that's the thing. If let's say I have a 1 molar solution of hydrochloric acid, and then I have a 1 molar solution of acetic acid, which is what these two equations are showing, okay? I have CH3COOH. So hydrochloric acid is a strong acid, okay? Acetic acid is a weak acid. So as long as I have equal concentrations, so notice they're both 1 molar, then this one is going to react faster, because even though their concentrations are both 1 molar, not all of the hydrogen from this weak acid are going to dissociate. So there's not going to be as many hydrogen ions in the solution in this second reaction. And so it will not react as fast as the first one will because of the higher concentration of those dissociated hydrogen ions. So the also relates to pH, and I kind of mentioned this earlier, that the strong acids are going to have a lower pH. So usually your strong acids are going to be down here, okay? Because they have a higher concentration of hydrogen ions, and that's what makes something more acidic. Our strong bases, they're going to be more up here in the 12, 13, 14. And then your weak acids and bases, the closer you get to neutral, the weaker it is. So, you know, your weak acids are going to be here, your weak bases are going to be here. And again, 7 is neutral, but, you know, the closer you get to 7 from either side, the weaker your acids or the weaker your bases get. All right, so the last section has to do with kind of applying acids and bases to sort of a specific area, and it has to do with sort of the environmental type stuff. It's called acid deposition. And so when something deposes, usually you're it's being deposited. And so we're talking about acid like kind of being deposited on things in nature or in substances. So a lot of this has to do with rain, like acid rain. Naturally, rainwater actually is slightly acidic. So rainwater, just because naturally there's carbon dioxide in the air, and carbon dioxide dissolves in water and it forms carbonic acid. It's a reversible reaction. So this is kind of like the same thing. If you guys remember when we did that that activity last semester with the soda, where it was like, you know, the carbonic acid would turn into carbon dioxide bubbles in water, and then the carbon dioxide bubbles, you know, if we increase the pressure, they would dissolve back and it would make more carbonic acid in the solution. So it's the same reaction. It's just we're talking about carbon dioxide in the air reacting with water and making carbonic acid in sort of the rainwater that's in the atmosphere. So naturally, rainwater has a slightly lower pH than neutral because of this naturally occurring carbon dioxide and the carbonic acid. What happens though is there are other substances, other gases in the air that can react and cause other acids to impact the pH of the water. And so that's where we run into what we call acid rain. And acid rain is between 4.5 and 5.0. So make sure you know that naturally rainwater is about 5.6. But acid rain is more like between 4.5 and 5.0. So it's got a lower pH. It's more acidic, okay? There's 2 different kinds of deposition. So the wet deposition includes both acid rain and also fog and snow. So all those kinds of different precipitation type things that involve water. Dry deposition There's a couple ones here. There's acidic gases, and there's also like solid particles. Okay. So some of the possible sources of deposition, this is kind of a good visual. Um, Power stations that give off sulfur dioxide gas. Sulfur dioxide gas can go up in the air and it can make sulfurous and sulfuric acid. Okay, and those are the two different acids that can lower the pH of that rainwater. Naturally, sulfur dioxide can come from volcanoes. So there's a word that they like to use, and it's right down here in this question. Anthropogenic. Anybody know what anthropogenic means? So anthropogenic means that it's man-made or it's caused by man. Okay, so man-made, or you could say caused by human activity. Okay, so things like power stations and transport, those are anthropogenic because humans are doing that. Volcanoes, not anthropogenic. That's naturally occurring. Like, we're not controlling the volcanoes. So yes, there's some of this naturally occurring just from things that happen on Earth, you know, with volcanoes erupting and giving off sulfur dioxide gas, but it's being exacerbated by things like power plants, power stations, cars that use fossil fuel and give off the fumes into the air. So in this like image, the power stations are anthropogenic and any kind of transport is anthropogenic. Volcanoes, not anthropogenic. That's naturally occurring. The transports that are going to give off nitrogen oxide gases, it could be NO2, NO3. Those are going to go up in the air and they're going to produce nitrous and nitric acid. Okay, so any of the compounds that contain sulfur are going to produce one of the sulfur acids. Any of the ones that produce nitrogen gases are going to produce the acids with the nitrogen in them. So here's what happens to form acid rain. If you have the sulfur compounds, they're either going to produce, like I said, sulfuric or sulfurous acid. Now, because we live in the United States, you'll see sulfurous spelled with the S instead of the PH, okay? And so those two acids that contain sulfur, they're formed when you have the combustion of coal that contains high levels of sulfur. So that's why things like power plants or power stations on this image, because they're burning things like coal. They're burning coal and oil and gas type of things in order to do whatever they're doing in that plant to create energy. And when you burn that, it's going to give off fumes and smoke that contain these sulfur dioxide compounds. Okay, and so basically the steps that you have here is you have sulfur, okay, solid sulfur, burning with oxygen, and it forms sulfur dioxide gas. Okay, then your SO2 gas, it dissolves in water, so it's going to react with the water, and when it dissolves in water, it forms the sulfurous acid, which is aqueous. And then SO2 can also react with more oxygen in the air, just oxygen gas, and that forms sulfur trioxide, SO3, okay? And let's see, this isn't balanced, so let's see, we'll put a 2 here and a 2 here. There you go, now it's balanced, okay? And then once you get sulfur trioxide, that sulfur trioxide gas can then dissolve and react with water to make sulfuric acid. So those are kind of the main processes that are happening here, is that the sulfur burned in the sulfur that's contained in the coal that's burned in these power plants reacts with oxygen gas in the air and it makes sulfur dioxide gas. Okay, then that sulfur dioxide gas itself can react with water vapor and make sulfurous acid, or the SO2, the sulfur dioxide, can react with more oxygen gas in the air to make sulfur trioxide, and then the sulfur trioxide can react with water vapor in the air to form sulfuric acid. Either way, your end result is one of those two acids that's going to lower the pH of your rainwater, and that's not good. for nature, for statues, for lakes, rivers, all that kind of stuff. The other version is this nitric and nitrous acid. So this is formed when you have nitrogen and oxygen reacting at high temperatures in internal combustion engines. So things like cars, machines, okay, airplanes, all the different things that we use to drive and get places, transport places, trains, okay. And so what happens is they have to be at high temperatures. So that's why the combustion engines, that's like the perfect place because they're really hot temperatures. And so what happens is you have nitrogen gas and oxygen gas reacting in that really high temperature. So usually you have heat. So you might see the little triangle symbol over the arrow, and you end up producing nitrogen monoxide gas. Okay, and we get 2 molecules of that, so it's balanced. Then what happens is then some of that nitrogen monoxide gas reacts with oxygen in the air, and it makes nitrogen dioxide. Okay, and then let's see, we need a 2 here and a 2 here to balance. And then that nitrogen dioxide is going to then react with water vapor in the air, and it's going to form either HNO3 or HNO2. Either one, it just kind of depends. And so that's our, I forgot my aqueous on the first one. Let me erase that. And then obviously you would need to balance them differently depending on if you get HNO3 or HNO2, okay? So the end result is through all these multi-steps, you end up producing these acids that are going to affect our environment, okay? So how do they affect it? Well, they can affect materials. So statues are made usually out of calcium carbonate, and carbonates react with acids, okay? Carbonates are one of the things we talked about that react readily with acids. And so when you see things like statues, old statues in ancient places, or even things like the pyramids, all these things are being affected by acid rain. And so the worse this gets, the more things like that are going to deteriorate. And so these 2 pictures are showing the same statue, just sort of like different years apart. And so you can see that it's kind of like worn down and some of the facial features are gone. You can't really see what it was before. It also affects our kind of environment, plants, water, okay, fish. And so acid rain, it's going to leach important nutrients out of the soil. So magnesium, calcium, potassium, these are ions that plants need. Plants need them to grow. Without the nutrients, they're not going to grow, and therefore you're not going to be able to grow things. So it can damage the roots of plants. It can cause like crops to not grow. And so that affects things like, food sources and the economy. And then it also releases aluminum ions from the rocks into the soil because it's going to react with some of the different compounds that the rocks are made of, the stone. And so then those aluminum ions damage the roots of plants, so they can't take up water and nutrients. So it takes nutrients out so they can't grow, but then it also releases these aluminum ions, which actually damages roots, and so they can't take up water and nutrients. So kind of a twofold problem there. With water, okay, if lakes and reservoirs are filled with water that has a pH of below 5, fish cannot survive in there, okay? So then you start having ecosystems that are interrupted. So fish are going to die off, and then all of a sudden food chains are interrupted, okay? Aluminum ions, again, same thing as with the plants you released, and that interferes with the operation of the fish's gills, and it reduces their ability to take in oxygen. And so that's why they end up not being able to survive in conditions like that. And so what's happening is you'll have aluminum oxide. It's going to react with the hydrogen ions from the acid, in the acid rain, and then it's going to produce these hydrogen ions and water. And those hydrogen ions, that's what's causing the problem, both for the damaging of the roots of the plants and also for interfering with the fish being able to breathe. The nitrates from nitric acid, they can also cause what we call eutrophication in the lakes. And so that's where they're going to have excessive plant growth, which is also not good. And then obviously it's going to affect human health as well, okay? Because eventually, like, we're all connected in the circle of life with the food chains and the ecosystem. And so whether it's, eating fish that have been contaminated with things, or whether it's just breathing in the acidic gases. So when we're breathing, it's going to irritate respiratory tracts. the mucous membranes in the nose and throat, all the way down to the tissues inside of our lungs. All of that's going to be affected. So it can increase your risk of respiratory diseases. That's why a lot of times, that's why they think that we're seeing more and more people that have things like asthma, bronchitis, and emphysema, especially asthma. A lot of people have asthma nowadays. And part of that could be because of the buildup of gases in our air that are from some of these things that we've talked about today. There's also a greater risk of some of these metal ions that are poisonous, like lead and copper, being released from water pipes, because if you have water that the pH is lower and it's more acidic, it could potentially corrode the pipes in our plumbing systems. And if they corrode it, that could be releasing some of these lead and copper ions. They usually use copper more now. Lead it was kind of older because lead isn't used as much, but there are still some buildings that probably have lead pipes. And so whether your pipes are made of lead or copper, either one, you don't really want it being released into the water. And so having the pH be lower is a risk, because if it's leaching or causing those metal ions to be released from the pipes, that's going to affect your water supply. And that's also going to, cause you to have potential health problems. Okay. So there are some solutions, okay, for how to reduce some of these emissions. There's two different ways they do it: pre-combustion or post-combustion. So pre-combustion means they're going to try to remove or reduce the sulfur that's in the oil or coal before they burn it, before they do the combustion reaction. And so the first one, hydrodesulfurization, it uses a catalyst, okay, so that speeds up the rate of reaction. And what it does is it removes the sulfur from the natural gas and all the refined petroleum products, so things like oil, okay? And when they remove the sulfur from it, that reduces the sulfur dioxide gas that's emitted when they burn the fuels. And therefore, that's going to probably obviously reduce the amount of those sulfurous and sulfuric acids, okay? So what they do is they will take coal, they'll mix it with powdered limestone during combustion. So this is powdered limestone. It'll create calcium oxide and carbon dioxide gas. The calcium oxide then will react with any sulfur dioxide, make calcium sulfate. If you have the extra oxygen, the calcium oxide will react with sulfur dioxide and extra oxygen, make calcium sulfate, which neither one of those are going to do any damage like the sulfuric acid or the sulfurous acid would. Now, post-combustion, this is after they've already burned the coal or the oil, okay, or the gas. So flue gas desulfurization, it can remove up to 90% of the sulfur dioxide emissions from power stations. So after the combustion's already taken place, they do a similar reaction. And so you can kind of see they do similar thing. You still have calcium oxide reacting with it. You get calcium sulfate, calcium carbonate with SO2, you get calcium sulfate and carbon dioxide gas. Calcium sulfate with oxygen, you get, or sorry, sulfite, and you get calcium sulfate. Okay. The last thing on here that it mentions is this catalytic converter. Catalytic converters are things that they can put onto cars in order to reduce some of the nitrogen compounds they release. So if you ever have an older car and you go to get it inspected and they say, well, it didn't pass because there's too many dangerous emissions coming off of it, you can actually go to a mechanic and they can install a catalytic converter on your car. And what it does is it will convert carbon monoxide, nitrogen monoxide to carbon dioxide, nitrogen. And then you go back and you get your car retested, and then they say like, okay, now it passes. And so what happens is the hot exhaust gases that are coming out of the car or the engine, they mix them with air and they pass them over either a platinum or a palladium catalyst. And that causes them to create carbon dioxide gas and nitrogen gas, which are not dangerous, or as dangerous at least as the nitrogen monoxide gases. Okay. And then the last one has to do with reducing the acidity of water. They can add powdered calcium carbonate to lakes because, again, carbonates are going to react with acids. So if the lake has a low pH, they can add powdered calcium carbonate to it, and it would react with some of the hydrogen ions and reduce the acidity, okay, and make it more, closer to what it should be as the pH level, okay. They can also use calcium oxide and calcium hydroxide for sort of the same thing, to neutralize the acidic water. So it's all about finding the balance in those levels between your acids and your bases. They do kind of similar things with things like swimming pools. So, you know, if you test the pH of a swimming pool and it's not where it's supposed to be, you can add different chemicals, and it will adjust the alkalinity or the acidity to whatever level you need it to be for it to be safe to swim.